Segment 27, Brightness and Luminosity. First, let's start with a few definitions. Luminosity is an intrinsic property of a star. It's the total amount of energy emitted by an object per second. The flux is something we can measure. It's the amount of energy passing through a square meter every second. That can be a quantity that's measured locally at the surface of the star, but it can also be a quantity that we measure here on Earth, very many billions of miles away from the star. Parallax, as we've seen, directly measures distance out to about 100 parsecs from the ground and about 500 parsecs from space. Once we know the distances, we can measure the flux of the objects and infer their luminosities. There's a relationship between the two quantities. The flux is equal to the luminosity divided by 4 pi times the distance squared. This implies that since it's luminosity we're trying to derive, flux is a measured quantity, and luminosity is an intrinsic quantity. The luminosity is 4 pi times the distance squared times the flux. The reason for this is that a sphere with twice the radius has 4 times the surface area, but the same amount of energy passes through it. This means that the flux will drop as 1 over the square of the distance. Let's look at an illustration to see how this works. If you start at a star, all the light from that star goes through any sphere that you surround it with. So the total amount of energy that crosses that sphere is then equal to L, the total luminosity. So let's look at this inner sphere at this distance. Let's just call it 1, distance 1, say 1 parsec. All of the luminosity from the star passes through a sphere at that distance of 1 parsec. If I draw another sphere at distance 2, say 2 parsecs, then all the luminosity passes through that sphere, but since the surface area of a sphere is 4 pi d squared, that second sphere is 4 times the surface area of the first sphere. And then a sphere that's at 3 times the distance has 9 times the surface area. So if you needed some number of tiles to put onto the first sphere, you need 4 times as many on the one that's twice as far away, or 9 times as many on a sphere that's 3 times as far away. So the same amount of luminosity, the same amount of energy per second, is going through 9 times as many tiles on this outer sphere as it went through on the inner sphere. That means that as we go 3 times farther away, the light is diluted by a factor of 9. So the flux, which is luminosity per unit area, or energy per unit area per unit time, is going as 1 over the distance squared. The actual equation then for the flux is the luminosity divided by the area of that sphere, or L over 4 pi d squared. So the thing to remember is that the flux drops as 1 over the square of the distance. Interestingly, it turns out that there's a possible, to a limited extent, to tell the luminosity of its star from its spectrum. And I apologize for the quality of this figure. The top line is supergiant spectrum, the middle is a giant spectrum, and the bottom is a main sequence star. And what you'll notice if you look at these spectra is that although they have the same temperature, these stars, so the line ratios are very similar, that the lines get broader and broader as you go to stars that are more like main sequence stars. So a supergiant star is a very big star, a giant star is a somewhat smaller one, and a main sequence star is more like the sun. The explanation for this goes back to the plot we made and when we discussed earlier about line formation in the stars. Remember that the line is formed above the photosphere in a region where the opacity is a bit higher, so that you're seeing into a slightly cooler region above the photosphere, and the absorption line forms there because that layer is a little less bright. And so at the wavelength of the line, you only look to that layer and you see less brightness, so the line forms at that particular point where the star is cooler. Or another way of looking at it is light is absorbed in that layer and then re-radiated in other directions at that particular wavelength. But the actual wavelength range over which this can take place depends on the pressure in the star's atmospheres, and stars with higher pressure can do this over a broader range of wavelengths, making the lines fatter. And stars with lower pressure in their atmospheres, the range of wavelengths is narrower, and so the lines are skinnier. And giant stars are more tenuous, so they have lower pressure in their atmospheres than main sequence stars, what astronomers rather perversely call dwarf stars, which have much higher pressure in their atmosphere, so the lines then will be wider. So by looking at the line shapes, we can infer something about the luminosity if we pick the right lines to do it.